Yes, thank you. So tolerable breathing loads, the trumpet curve and beyond. My current work title here, as you can see, is Senior Research Engineer. Depending on where I worked, it's been Senior Research Scientist. When I was in Buffalo at Department of Physiology, I was also a Research Assistant Professor in Respiratory Physiology. So I like the combination of engineering and breathing. So in a way, you can say what happens when the rubber meets the face. Not anything else, but so the combination of respiratory physiology and engineering. And you have my emails on the lower left there as well. And there we are. And the usual statements that these are my opinions, not necessarily the Navy's, and I am a contractor working for the US government and so on. So the trumpet curve on the right, you have an early version of it, and I'll go into more details shortly. So I will talk about what the trumpet curve shows, where it came from, its origin, how it compares to other limits for respiratory protection, and steps beyond it. So in military aviation, we have this trumpet curve that dates back to 1980s or so, and here you see it as two red lines. The top line shows the pressures that are allowed during expiration, and the lower ones here, what the pressures allowed during inspiration. And here it goes up to minute ventilation of between 60 to 65 liters a minute, or peak flow of 200 liters a minute if you have sine wave breathing. And you don't necessarily need to look at the numbers specifically in this talk, because I'm looking more at shapes and such and limits. But you will find out what that is. And if you compare it to limits set by NIOSH certifies respiratory protection devices for occupational use when you filter out dust, paint fumes, whatever you want. Even COVID-19, the famous one, N95s, are tested and certified by NIOSH. So overlaid on the trumpet curve, you have some of their limits. Pressure demand system, if you have a gas mask, you allow these pressures. Closed circuit device, this limit. If you have an escape device, you can tolerate higher limits, apparently. And if you had other industrial limits based on the European standards, you have CO filters, carbon monoxide filtering devices, and various other limits. And they are not consistent. If you have this particular device here, you can tolerate this much pressure swing. But at the lower work rate, suddenly you can take more than twice as much pressure. And so it's very confusing. Why are they so different when the same person may be using each type? Does your strength of your muscles change just because you put a different mask on your face? Of course not. And if you look at, so these were plotted against the pressure swings, the peak pressures. If you look at limits set by worker breathing, which is really the mean pressure, not the peak pressure, but I'll talk more about that later. They are all over the place. And here are some that go from 0.5 joules per liter up to 4. Others in the same situation only allow 1, so factor 4 different, or 0.5 to 2.5, so factor 5 different. How can that be? And people don't change. And if you look at NADU, which is the Navy's experimental diving unit, this is a scuba regulator. They can take 1.37 joules per liter, but if you're breathing from a tank on your back, if you get breathing gas from a hose coming from the surface instead, this limit applies, which is 15% higher. Do you get stronger because you get the gas from the surface? Of course not. And you can also be silly and look at the category 4, which is a rebreather. Or do you become a weakling just because you breathe on a rebreather? You have to think which one is correct. They can't all be correct. And the real reason is that essentially all devices and probably all limits were set on performance based on a certain device. Somebody had built a gadget that was good enough, it seemed, to breathe on, and that became the limit. Not necessarily based on people's tolerance. Go back to the trumpet curve again. Was this based on people's tolerance? If you do a curve fit of these two, you get the second order polynomial. I mean, it's laminar and turbulent flow, so it makes very good sense. And if you look carefully, you look at the fits of these. I mean, R squared of 0.99999 is absolutely fantastic, but you never see that in human subject testing. 0.9 would be wonderful, and this is 1,000 times better. It looks as if the data originated from a breathing system, and the data that were collected were fitted to a polynomial, and the results of that polynomial fit was put in a table. And if you read the Ernsting's justifications or historical description of where it came from, it says like this: this UK standard, which I haven't been able to find because it's not referenced in the document, was adopted by the Air Standards Committee and NATO nations in the early 1980s as being the best compromise between physiological requirements and equipment design, which can be achieved using current technology in the 1980s. That's 40 years ago. And he continues, compares the limits proposed here to another set of limits that the external respiratory work was recommended by Morrison and Reimers. And what Morrison and Reimers wrote in that paper, and first of all, you can see they proposed this brown line here. So somewhere in the middle of all the other lines. And they wrote that in these circumstances, it is fair to say that there are inadequate physiological data on which to base reliable performance standards for underwater breathing apparatus. That's what they wrote it for, but all the data they used came from experiments on dry land. So the numbers really came from just dry land. And there's an urgent need, therefore, to accurate tolerance testing of diverse equipment. And they finish up with saying that suggested standards can only be regarded as an interim measure and subject to change. 1982. What has happened in the last 39 years? Well, there's a new compilation of previous studies and including new data. And I know I'm one of the authors on this, so it's not, I think I still can be objective about it, but it's the best we have to date. Is it the final answer? I hope not.
417 West Ottawa. Arrival time on this route is similar to Terry Fox Drive, Carp Road, Ottawa.
Somebody's voice came in now. And we added new data, particularly at high work rates. And then, as we discussed earlier, the limits have been adopted in the ISO's respiratory protection document in 2012. So we have new data there. And what has happened in terms of engineering? Well, since 1982, we have computer-aided design. We have solid modeling of this. We have computational fluid dynamics. We have much higher precision manufacturing. We have 3D printing, including in metals, as we saw at the meeting 2 years ago when we went on a tour. So we know more and we can do more. So I think we can safely tighten up a few things if we need to, based on people's needs. And one thing we have to ask ourselves, what should the shape of the limit be? In the graph on the right, you see there are constant values, independent of minute ventilation, just horizontal lines. There are some that go up with flow in a linear fashion, and then some that go up with the square of the flow, which is the appropriate set. And there are two ways you can look at this. You can consider the workload necessary to breathe, as in by the muscles. But with increasing workload for the entire body, the minute ventilation increases in proportion. It would make physiological sense if the increase in the workload for the respiratory muscles matches the increase in workload for the rest of the body. So if the legs work harder, your respiratory muscles work harder in balance. So you can write that out mathematically. The change in the respiratory workload is the constant times the change in the body's whole body workload. So you take that equation again and rewrite it. The power is voltage times electrical flow, normal and current, or pressure times flow. But the power of the workload is then the worker breathing times the flow, where worker breathing is actually the average pressure. So if you have a proportional increase in workload, it means that worker breathing has to remain constant. Or put differently, limits to pressure, average and peak, have to be independent of minute ventilation. You can also think of it in another way, the alternatives. We saw that the pressure limit increased linearly with flow. That would mean that the flow goes up and this would go up at the same time in proportion, which would mean that the power requirements will go up with the square of the flow. So if you double the flow, are the muscles suddenly able to do 4 times the work? Or the pressure limit that increased with the square of the flow, it means that the respiratory workload will go up the cube of the flow. So if you double the flow, suddenly the muscles can take 8 times the flow. These alternatives are not realistic. So the pressure drop should be a constant value. And if you look at combine the trumpet curve and the physiological limits combined, the blue line is then the numbers from the 2012 paper, and the black are the numbers from the trumpet curve, and here shown as with the extension in 2015 to a higher work flow rate, not 200 liters a minute, but 258, but the pressure status did not increase. And if you combine them to so we selected the values that are best for the user or the breather. So you get limits like this. So we keep the trumpet curve at the lower flow, but reduce the pressure allowance, so to speak, at the higher flows. And if you had safety pressure, it would look like this. Safety pressure is really just an offset. And in terms of limits on the average pressure or worker breathing, it would look like this for inspiratory and expiratory sides. And if you have now come up with something totally stupid, if you do a reality check, where does existing equipment fit into this picture? So in yellow here, you see an older design of a breathing system, regulator, mask, hose and mask, and the inspiratory average pressure follows this line, the expiratory this one. And a newer design, the expiration was about the same, but the inspiratory side, it went down much better. So in this range here, it went from about 3 inches of water down to under half. So an improvement of a factor 5. So a much, much better design on the inspiratory side. Interestingly, if you now look in the range where aircrew typically breathes, in the low 20s or so liters a minute, we see that the pressures from inspiration and expiration in the old design were very similar. So sort of a balance. It was just as hard to inhale as exhale. If you look at the newer design with a much better inspiration, the expiration pressures are 3 to 5 times higher in this typical range. So there's an imbalance, and would be quite noticeable to the aircrew. It's like carrying home groceries. You have one heavy bag in one hand and you have 4 bags of heavy groceries in the other hand. You feel the imbalance very distinctly. And I know my back would complain about it, but that's a personal problem. And some pilots have been reported as saying that it's too hard to exhale, and would like to blame it on the safety pressure. But it may not be safety pressure at all. It may simply be that it is harder to exhale than to inhale, and but because of the resistance in the mask in this case. And I have tested one particular breathing system, and half of the total resistance in the system was in the mask. So it's very localized. It was not a regulator in an older design. It was actually half the resistance was in a mask. And you can add up the pressures that are generated in the mask as a part that consists, well, depends, I should say, on flow resistance times flow, and elastance times the volume change, and the constant pressure. In mathematical terms, the pressure is resistance times flow, plus elastance times the volume change, plus a constant. And this constant has many names, like a dear child called many things. In military aviation, it's called safety pressure. In diving, it's called hydrostatic imbalance, or static lung load, if you like. In firefighting and SCBA use, it's called positive pressure. And in anesthesiology, it's called PEEP, for positive and expiratory pressure. It's really all the same thing, just different names depending on what field you're working in. And how do you set limits on other respiratory loads, not just flow resistance? Well, we know that there's elastance in a system like a rubber band. It takes effort to stretch it, from hoses that expand or contract, and masks that may buckle on your face a bit or move depending on the design of the mask. We also have these static loads or constant loads that are safety pressure. We have empirical maxima on the elastance, which is 1 kilopascal per liter, 10 centimeters of water per liter, or 4 inches of water per liter, depending on your favorite unit. We also know that static pressure, as in this case, the positive side, people can tolerate 10 to 15 centimeters of water if there's no other load around, or 4 to 6 inches of water. And that's actually a very practical and easy way to add these loads up. When you have apples, how do you add up apples, oranges, and bananas? But you know when the fruit bowl is full. So how do we do this for low respiration? The breathing resistance tends to act in the middle of the breath when the flow is the highest. But an elastic load comes in at the end of a breath when the volume change has been the biggest, but the static is always there. And based on lots of experimentation, we can say that if you can add up the relative resistance plus the relative elastance and the relative constant pressure, that tells you the percentage of the load you have at the moment. And this may sound complicated, but I'll show you an example. So if, say you have in a certain situation, the pressure drop due to resistance is 5 centimeters of water, and in that situation, your load 12. So the resistance load is 42% of its maximum. And the elastance measured in that situation was 1 centimeters of water, but you load 10, so that was 10% of its load. And the static was 3.8 centimeters of water, 1.5 inches of water, and you allowed this much, 15 or 10, so it's depending on which limit you use, 25 to 38% of its maximum. And the total load is just then the sum of this, and this. So you add them up like this. So the total load of this situation was between 77 and 90%. So as long as you stay below 90%, you should be okay. And our other respiratory loads, you may have odd or unexpected behavior of a breathing system. You may have volume or flow limitations. If you have a low pressure coming to the regulator, it will not give you much gas. It may give you 1 liter a second, but if you try to get 1.01 liters a second, you're not getting it, no matter how hard you pull. And that can upset people and make them breathe in funny ways. You may have threshold loads that you have to generate a certain pressure before a valve, say spring-loaded valve, opens, and then you can breathe freely. You may have pressure bursts from the regulator. It just raises the pressure and maybe too much and tries to push gas into you. You may have sticky valves that sort of, once the pressure is open, it pops open and then it's open again, free to flow, I mean. And you may have other nonlinear function of a regulator when the supply pressure is low. I mean, the regulator may not have a chance, simply. And also not really related to the breathing system, gear fit that limits chest expansion. If you have heavy equipment on your chest and the seat leaning back, you may have loads that way, but that's beyond this particular topic here. So in summary, the trumpet curve represented a compromise between people's needs and what could be built in 1982. Today, we know people's needs and abilities better, and the manufacturing abilities are far better. We saw the improvement in a regulator by a factor 5 in inspiratory resistance. The respiratory loads, that's in peak or mean pressures, elastance and static pressures, can be assessed separately, and then the total load can be added up. And military standards and other standards of this type will need to be revised continuously as more information becomes available. So what we know today in terms of respiratory or breathing resistance tolerance should change in the future, because it is not the final answer. And thank you.